This is part 2 and Mr. Erlin talking about honors pre-calculus midterm test prep. We just worked on number 9 before I was interrupted. We were given a series of zeros, 3, -3, 2 plus I, 3 minus 2 root 2, and we were asked to write a polynomial function in standard form. So we create all the factors, x minus 3, x plus 3, x minus 2 plus I. And because that's a complex term, we know that there has to be a conjugate pair. If there's 2 plus I, there's also 2 minus I. So I'm going to put x minus 2 plus I and x minus 2 minus I. Similarly, if we have an irrational solution like this, 3 minus 2 root 2, we can expect that we're going to have x minus 3 minus 2 root 2, as well as x minus 3 plus 2 root 2. Conjugate pairs will make the irrational components and the imaginary components disappear when we follow this out, when we distribute. So x minus 3 times x plus 3 is a difference of squares, x squared minus 9, no problem. X minus 2 plus I and x minus 2 minus I becomes x squared minus 2x plus xi minus 2x minus xi plus 4 plus I. And as I clean that up, it becomes x squared minus 4x plus 5. Again, the imaginary components have dissipated because we used conjugate pairs. Similarly, with our irrational terms, we get x squared minus 3x plus 2 root 2x, 2x root 2, and minus 3x again, and then minus 3x minus 2x root 2, and then a plus 9, which is 3 squared, and a minus 8, which is the 2 root 2 squared, difference there being 1. So x squared minus 6x plus 1. Now, when we FOIL this mess together, what I like to do is take this term times this term to make this term. No problem. And then I'm going to use the x squared across each of these terms. So x squared times negative 4x is negative 4x to the third. X squared times positive 5 is positive 5x squared. When I take the 9 across this, I'm going to move it down a line, aligning my x squared terms so that I can just add vertically to simplify. So negative 9 times x squared is negative 9x squared. Negative 9 times negative 4x is positive 36x. Negative 9 times positive 5 is negative 45. And what that gets me is these two combined, x to the fourth minus 4x to the third minus a net of 4x squared plus 36x minus 45. And we still have to distribute this piece through. So let's do that. Again, I'm going to take x squared and distribute it across all of these. I take the smaller number of polynomial pieces. In other words, the trinomial instead of the 1, 2, 3, 4, 5 quintinomial. So x squared times x to the fourth is x to the sixth. X squared times negative 4x cubed is negative 4x to the fifth. Negative 4x to the fourth plus 36x cubed minus 45x squared. And now I'll do the negative 6 components. So negative 6 times x to the fourth is negative 6x to the fourth. I'm going to line that up with x to the fourth. Plus 24x, oops, excuse me, that was the fifth. X times x to the fourth is x to the fifth. So negative 6x to the fifth minus 24x to the fourth plus 24x to the third minus, what is that? 180 and 36 is 216x squared. 45 times that is 3 times 90 is 270, so plus 270x. And now I have to do the 1. So positive x to the fourth minus 4x cubed minus 4x squared plus 36x minus 45. And combine all those. X to the sixth minus 10x to the fifth plus x to the fourth. So this is minus 28 plus 1 is minus 27x to the fourth. 60 minus 4 is plus 56x to the third. 216 and 4 is 220, so minus 265x squared plus 306x minus 45. Whew, that's the polynomial that had those original zeros of 3, negative 3, 2 plus I, and 3 minus 2 root 2. Number 10, a polynomial is shown in factored form. P of x equals x minus 2, x plus 3, 2x minus 5, and x plus b if the point 0, negative 60 is on the graph of p of x, what's the value of b? Okay, so in order for it to be on the graph, what that means is that the point 0, negative 60 is a solution to this. So if I make an x value of 0, p of x would be negative 60. So I'm going to create the equation. Negative 60 equals 0 minus 2, 0 plus 3, times 2 times 0 minus 5, times 0 plus b. Well, this just makes negative 2, positive 3, 0 minus 5, and b equals negative 60. So negative 6 times 5 is positive 30. Negative 60 equals 30b. If I divide by 30, I get that b is equal to negative 2. Okay. Number 11, a polynomial in factored form, and we're supposed to graph this. Okay, and we're just going to do a sketch of this. I see some zeros here. I see zeros at 2x equals 0, so 0, x minus 3, so 3, x plus 3, so negative 3, and this one's got a multiplicity of 2 and 4 minus x. In other words, 4 minus x equals 0, so 4 equals x. So these are my zeros. I'm going to plot them. I've got a x-intercept at 0, I've got an x-intercept at 3, got an x-intercept at negative 3, and it's actually a multiplicity of 2 there, and then x-intercept of 4. Overall, when I multiply this function out, if I look at just the x terms, I'm going to get 2x times x times x times a negative x. So 2x squared, x to the third, x to the fourth. It's going to come out with negative 2x to the fourth. And rather than have to multiply that whole mess out, I do know that the last piece is going to be minus 60 because the y-intercept is 60. But I know the lead term is negative 2x to the fourth, and that tells me what the function looks like. Even exponents mean that it either looks like that for an x to the fourth, or if it's a negative lead coefficient, it looks like that. So in this case, I want my end behavior on both sides to be approaching negative infinity. So I'm going to come up here. Because this is a double root, in other words, this one shows up twice. Let me do this 2, 3, 4, 5. This is a fifth degree. Oops. Good thing I checked that. This is going to be 2x to the fifth, right? Because this, ooh, I made a mistake there too, didn't I? Because the x plus 3, this one shows up twice. Look at that. Tricky one. So this 0 plus 3 shows up again as 0 plus 3 because it was squared. So I've got another plus 3, and I've got a negative 5. So I'm going to get 2 times negative 3, positive 3 makes negative 6, plus 30, 90. So negative 60 equals 90b. Divided by 90, divided by 90. So negative 2/3 equals b. Okay. And when I look at what happens to the overall function in terms of end behavior, 1x, 2x, 3x, 4x, 5x, it's an x to the fifth. And because I've got a positive x here, positive x here, positive, positive for these two, this is a negative, I'm going to get negative 2x to the fifth. So it's not going to be those shapes. Those are for even functions. This is an odd function. So if it were a positive x to the fifth lead coefficient, it would look like this with, as you approach negative infinity, f of x would approach negative infinity, and as you approach positive infinity, f of x would approach positive infinity. But because this one's negative, it's going to be the other direction. It's going to look kind of like that. So I'm going to come over here, and I know that I have to come from the positive side up here, and I'm going to hit that double root, and it's going to bounce rather than go through it. It's going to come down through this root. It's going to go up, come down. It's going to end up something like this. And I have no idea about the relative or local mins and maxes. I'm not addressing those at this point. I'm just sketching what it looks like. That's what we're looking for 11a. 11b, a rational function with a slant asymptote. Okay, so here's an example. That was 11a. So if I've got g of x equals x to the third minus 5x squared plus 6x over x squared minus 9. What I want to do is factor the top and bottom. So on top, I'm going to factor out an x. I'm going to get x squared minus 5x plus 6. On the bottom, I see a difference of squares, so I'm going to call this x minus 3, x plus 3. And then I'll keep going with this here. I'm going to factor this further. So this is now x. This is x minus 3, x minus 2 over x minus 3, x plus 3. All right, and so now I'm going to look at the details involved with my factored form. I'm going to first identify holes because these two cancel out. I know that there's a hole at x minus 3 equals 0, which means x equals 3. And I'll fill that in later. It's going to be 3 comma something. I don't know what that's going to look like without plugging it back in. I also see that my denominator x plus 3 is going to be a problem if this ever equals 0. So that's going to give me something called a vertical asymptote. I know that x plus 3 cannot equal 0, so x cannot equal negative 3. So 1, 2, 3. I'm going to give myself a vertical asymptote there. I also am going to look for either a horizontal asymptote or a slant asymptote. It's going to have one or the other, not both. And what I look for is to identify which degree is larger in the top or the bottom. So this is a polynomial written in standard form with the biggest degree out front, as is this. When I compare the 3 to the 2, I see that it's top heavy. Whenever it's top heavy, that's calling for a slant asymptote. Whenever they're balanced where the degrees are the same top and bottom, you look at the lead coefficient. It's a horizontal asymptote with y equals a ratio of the coefficients. Whereas if it's a bottom heavy, where the denominator's exponent is larger than the numerators, then it's going to have a horizontal asymptote at y equals 0. In this case, because it's top heavy, just as we expected, since it said a rational function with a slant asymptote, we're going to have to find a slant asymptote. So I'm going to take my function x cubed minus 5x squared plus 6x. Actually, no, I don't. It would be better for me to cancel those out, make life easier. That's a whole, so that doesn't really affect the whole thing. So now my inner is actually x squared minus 2x, and I'm dividing it by x plus 3. So let's get rid of that part. And for long division, I'm going to say x goes into x squared, x times x is x squared, x times 3 is plus 3x. When I subtract here, this goes away, this becomes minus 5x. And so in other words, this whole function is a rational function. We call it g of x. G of x can be expressed as x plus this remainder, negative 5x over x plus 3. That's the simplified version of it. When I take this divided by this, I get this result. It's not g of x. Or multiplying this whole thing by x plus 3, that would be g of x. But what this tells me is that x is my slant asymptote. In other words, this function is equal to x plus 3 that we divided by times x plus this thing, negative 5x over x plus 3. This is a remainder, effectively. And that shows me how far away my graph is from this line, y equals x. So I'm going to graph that as my asymptote, y equals x. And I know that the graph is never going to quite hit that because no matter what value of x I have, I'm always going to get something really, really close. Except, of course, at x equals negative 3 in the bottom, which would be this vertical asymptote. And when it's 0, that's going to be one of our x-intercepts. So that's not a huge surprise either. Okay. Now we have to graph this. Oh, we need our x-intercepts. So x-intercepts happen when the top is equal to 0 and not canceling out. So that would be x equals 0 for this one, and x minus 2, which leads to x equals 2. So I know that at 0, I've got an intercept. That's interesting. It's also on the slant asymptote, so we'll have to double confirm that in a second. And then we get x equals 2 is another one. That's really raising some questions for me right now. Okay, x and what about our y-intercept? Y-intercept is going to happen when the x is equal to 0, and because we've got an x on top, it's just going to be 0 over something. So again, the y-intercept suggests 0, 0 is a coordinate there. All right, what do we do about graphing? Well, we know that something is going to be happening over here, but there's not going to be any intercepts. There are no y-intercepts. Excuse me. Okay, so over in this region, we're looking for x-intercepts. We don't see any. Our only x-intercepts are at 0 and 2. So we don't expect it's going to be over here to cross over this. Therefore, if it came asymptotically along this asymptote and came down to cross over, it would be crossing here. It's not. Therefore, we know that it's not doing that. Instead, what we have is this intersection here between y equals x and x equals -3, and we're expecting to see a function that runs up like this. It's going to be trapped down here in this little quadrant. Again, we don't know what the maximum is yet. Turns out it's going to be something like -15, but for right now, we don't really care about that. Up here, this is more challenging. We expect it to be, since it ended here on this asymptote, we expect it to start on the other side. And it could start here, but then how would it cross over here and come back down here? It could also start up here, in which case it could come down, cross over here. And it turns out that's what it's doing. Pretty crazy one. It comes down, we'd test points, and we'd come back up here, and we see that it's actually asymptotic from the underside like that. So this is the sketch of our graph that has an asymptotic slant asymptote. Note, this showed up a couple times. We saw it as a y-intercept. We saw it as an x-intercept. We also could have tested that by saying, now, wait a minute, does this actually work? In other words, does my whole function ever equal 0? So if I take the function and set it equal to 0, I'll use the simplified form. So I'm going to get x times x minus 2 over x plus 3. When I cross multiply, I end up with 0 equals x times x minus 2, right back where we started from, saying that there are two values where this could cross over the axis, x and 2. And yeah, since we've set this equal to 0, y equal to 0 in this case, what we're really finding is the same as the x-intercept. So this matches with what we saw before. Pretty challenging one. Okay, let's go to 11c, a log that is transformed. We're graphing again. We know that typically the parent function of a log goes through this point 1, 0. And then if, for instance, it's log base a of b, so when we're looking at log base a of x, if this base is a, then that means that this point 1, 0 is always on the graph. And when you go up 1 unit, it goes over a units. When you go up 2 units here, it goes over a squared units. Okay, so what we're expecting to see as a parent function is something kind of like that. This one's going to have transformations. Transformations of this one are right 4 units and up 3 units, and a horizontal 1/2 makes us, oh, it's on the outside though. So it's a horizontal, nope, it's a vertical. Vertical compression, factor of 1/2. So what I'm going to do is I'm going to create the parent function of y is equal to log base 2 of x. I'm going to create the x and the y values. Let's pretend I don't know these. That means what I'd want to do first is find the inverse functions, x and y values, the critical values for the y equals 2 to the x, because log and exponents are inverses of each other. So I know that if I put in -2, -1, 0, 1, 2, this would come out 2 to the -2, which is 1/4, 1/2, 1, 2, and 4. And because these are inverses, I know that my log values, when I have an x value of 1/2, my y is going to be -2. 1/2 is -1, 1 is 0, 2 is 1, 4 is 2. And this should match what I've got here. 1, 0 is here. 1/2 would be at -1. 1/4 would be at -2. When I go over to 2, it goes up 1, because that's what my a is in this case, base 2. When I go over 4, which is a squared, it goes up 2. But what I've got going on is these changes. So I'm going to do a transformation table. And to my y values, what I'm doing is I'm multiplying by 1/2, and then I'm adding 3. So my y values are going to be 1/2 y plus 3. My x values are going to be adding 4. It's the opposite of what we see in there. So x plus 4. So I'm going to have 4 1/4, 4 1/2, 5, 6, 8. And then this is half of that plus 3. So -1 plus 3 is 2. -1/2 plus 3 is 2 1/2. 0 plus 3 is 3. 1/2 is 3 1/2. 1/2, 2 plus 1 is 4. Okay, so that half skipping there reflects the nature of that vertical compression. So what I'm expecting to see here then, I'm going to scale by halves here. So I'll go 1, 2, 3. And I'm going to go 1, 2, 3, 4, 5, 6, 7, 8. So I've got the point 8, 4. I've got the point 6. No, I'm going by halves here, aren't I? I need more. So 1, 2, 3, 4. 1, 2, 3, 4, 5, 6, 7, 8. -1. So I know that I've got the coordinates of 8, 4. 8, all the way up there at 4. I've got 6, 3.5. I've got 5, 3. I've got 4.5. Yep, 4.5 is up 2.5. 4.25 is up 2. And I had this whole thing shift over to the right 4 units. And so whereas my original one had this vertical asymptote on 0, I'm expecting to see that vertical asymptote coming right down here at 4. And whereas this point of 0, 1 used to be here at 1, 0, excuse me, not 0, 1, it's 1, 0. Now it's moved over to the right 4, so it's at 5. And it's also moved up 3, so it's up at 3. So it's at the point 5, 3. My graph would look something like that. All right. Number 12, radioactive decay. The initial quantity present in carbon-14 is 800 grams, which has a half-life of 5,730 years. Okay, so the first thing I have to do is recognize that it's an exponential decay. So A equals P times e to the RT. It's some version of that, and everybody's got these different versions. A of t equals a of 0 times e to the kt, something like that. They're all different versions, but they're all the same structure here. They're exponential decay. Now, what we know is that it has a half-life of 5,730 years. What that means is that whatever my preliminary amount was, my principal, my resulting amount, my after, is going to be half as much. So I'm going to make it easy. I'm just going to say if 10 is my starting amount, I know that I end up with half as much, 5, with my unknown r or k, after 5,730 years. That's my half-life. And so when I divide here, I'm going to get 1/2 equals e to the r times 5,730. Take the ln of both sides. I get ln of 1/2 is equal to 5,730 r. So my rate of decay is ln of 1/2 divided by 5,730. And some people call that a k, or some people call that an r. My equation, I said leave the k precise. That's what I meant. And now I need to find the amount of the substance after a t value of 150 years. So now I'm coming back to this, and I'm using my new r, my new k, and I'm putting in a t of 150 years, starting with 800 grams. So now I'm looking for the amount at the end, starting with 800 grams, with this decay rate and a time of 150. And that's just now a plug into the calculator and solve that. So I'm going to go with 800 times e to the, in parentheses, I'm going to do an extra parentheses, ln 0.5, close that, divided by 5730, close that, times 150. And I get 785.61. What are the units on this? These were grams. And does that make sense? We started with 800 grams. We know that it takes 5,000 years to get cut in half. This is like 1/5 of that, so it's not going to get cut in half. Yeah, it's going down, but it's not substantial amounts. That seems reasonable. All right, 13. Anthony, a recent TAM grad, decides to save his money by attending College of Marin for 2 years before going to a 4-year university. Anthony invests the $60,000 at age 20 in the S&P 500. The average rate of return in the S&P 500 since 1970 is 11.2%. Assuming the same rates of return, how much will Anthony's investment be worth at age 65? Okay, so this is not a PERT or continuous growth. This is going to be assuming some annual payment of interest. Yeah, it doesn't specify. So I guess we'll just go with A equals P times 1 plus R to the N to the T. Because we're saying N is 1. Effectively, you only get paid interest once a year. Okay. He started with $60,000. So P is equal to 60, 1, 2, 3. And the R rate is 11.2. So I'm going to say 0.112. And the time is going to be 65 minus 20. So it's 45 years. So 6123 times 1 plus 0.112 raised to the 45. So and I put an extra zero there, or just an extra zero. It's 60,000. 60,000. That's 6,000. 60,000 times 1 plus 0.112 close raised to the 45 years is 7.126 million. $7,126,342.26. Well, that's a healthy return on not going to college for 2 years, isn't it? But the stock market isn't a guarantee. What rate would he have to average to end up with $5 million at 65? In other words, he can earn less than 11% and still get 5 million because now he's targeting to get 7 million. So again, if I start with $60,000, 1 plus R to the same 45, but I want to find out when that equals 5 million. So I'll take 5 million, I'll divide both sides by $60,000. 5, 1, 2, 3, 1, oops. 5, 1, 2, 3, 1, 2, 3, divided by 60. And I get 83 and 1/3 is equal to 1 plus R to the 45th. I want to get to R, so I have to get rid of this 45th exponent. I'm going to raise both sides to 1/45th. So if I take this raised to the parentheses 1 divided by 45, I get a very small number, 1.103277754 is equal to 1 plus R. And so if I subtract 1, I get R equals 1.0327777536. So as an interest rate, in other words, that's 10.33%. If I earn 10.33%, I'll get $5 million. If I earn what the stock market's been returning of 11.2%, I'll earn $7 million. Okay. How much more money would he make if he started the investment at age 18? Okay, we'd started at 20, so starting at 18 is 2 years earlier. So all that would do is change this. Instead of it being 45, we'd make it 47. So I'm going to take this equation and say, how much more money would he make? Instead of making $7 million, what if instead we had said 60,000 times 1 plus 0.112 raised to the 47th? So only 2 more years. This one's at 7.1 million. Now if I do 60, 1, 2, 3 times parentheses 1 plus 0.112 close parentheses raised to the 47, we're just keeping in for 2 extra years. And now I make 8.8812035.76. So in those last 2 years, I make an additional $1,700,000. We're just keeping it in 2 years. Wow. If start at 18. All right. Money in the future is worth less due to inflation. Use the formula for net present value. NPV, net present value, is equal to future value divided by 1 plus R to the T to calculate how much $5 million in 45 years is worth today. Assume inflation of 2.5%. This is a cool equation. So what this says is if I want to figure out how much a future payout of $5 million is, right now it's worth less than that. Well, it's got more spendability now, which means if I had something like $2 million now, it would be worth the equivalent of $5 million in the future because $5 million now has an impact to inflation. It can buy less, so it's worth less. So if I take the future value divided by 1 plus r to the t, in other words, I'm taking this $5 million future value, and I'm saying how much is that worth in today's dollars, assuming there's an inflation rate of 2.5% over 45 years. So I'm going to take $5 million, divide it by 1 plus 0.025 raised to the 45 years. 5, 1, 2, 3, 1, 2, 3, divided by 1 plus 0.025 raised to the 45. And I get 1645872.02. So, in other words, getting $5 million in 45 as your eventual payout, that sounds like so much money. And it's a lot, but it's equivalent to $1.646 million today. So yes, you'd be a millionaire with those $5 million, but having $5 million today would be worth a lot more. And we could do this backwards. We could say if we have $5 million today, what would be the future value at that same rate of return where we've got this 2.5%, 0.025 over 45 years of an inflationary loss. So now we'd be multiplying both sides by this. We'd take 5 million times 1 plus 0.025 to the 45 is equal to future value. Oh, well, that just looks like our regular investment equation, doesn't it? A equals 1 plus r to the t. So if we do 5 million times parentheses 1 plus 0.025 to the 45, 15189,516. So in other words, if we did an investment to make $5 million in 45 years, it would be equivalent buying power to having $1.6 million now. In the future, $5 million would be worth so much less that it's the equivalent of $1.6 million now. On the other hand, if I take $5 million now and I figure out what its loss in value is due to inflation, in other words, how much less buying power it is, how much money would I have to be an equivalent buying power? I'd need $15 million in the future. My future value of $15 million is equivalent to $5 million today. Interesting stuff to talk about. Okay, number 14. Solve for x, leave your answer precise. So I've got 4 to the x plus 2, 16 to the 3x equals 1/2 to the x plus 6. I need these all to be in the same exponent. And I saw a lot of people try to do things like, okay, I'll make them all in 2s. So it's going to be 2 squared x plus 2 times 2 to the 4th to the 3x equals 2 to the negative 1 to the x plus 6. So I simplify that to make 2 to the 2x plus 4 times 2 to the 12x equals 2 to the negative x minus 6. And the mistake that I keep seeing people do is they just cancel all these 2's. I don't know if they're logging by base or if they're multiplying by a 1/2 or if they're dividing by 2 or if they're taking a log base 2. I don't know what they're doing, but you can't do anything with these as they're multiplied at this point. So instead, you have to recognize that if I have a to the x times a to the y, multiplying with the same base means you add the exponents. So over here, this is going to become 2 to the 2x plus 4 plus 12x. We're adding these exponents together, equals 2 to the negative x minus 6. And now that we have a single base that's common to both sides, I could take the log base 2 of both sides, which means I'm going to get this as now a combined exponent 14x plus 4. And I can pull that out front and say 14x plus 4 times log base 2 of 2 equals, bring this out front, negative x minus 6 times log base 2 of 2. Log base 2 of 2 is 1. So I'm left with 14x plus 4 equals negative x minus 6. So in other words, at this point, I could have just canceled those 2's and gotten to this. I'll add one more, so 15x, I'll subtract 4, is equal to negative 10, so x is equal to negative 2/3. Okay. Let's take a look at 14b. Log base 4 of 2x plus 7 plus log base 4 of x equals 1. When I add two logs together, I can treat that as a single log, where the arguments, 2x plus 7 and x, are multiplied. So I'm just cleaning up this left side a little bit. That's going to give me log base 4 of 2x squared plus 7x equals 1. And now to solve this, I'm going to take it out of out of log form and move it into exponential form, effectively by going 4 to the on both sides. 4 to the log base 4 of this, these parts are opposites of each other, inverses. So I can just get the exponent. 2x squared plus 7x equals 4 to the first, which is 4. So 2x squared plus 7x minus 4 equals 0. I get to apply the zero product property. I know one of my terms is going to be 2x, the other one's going to be x. I need their difference to be 7. One's going to be positive, one's going to be negative. So I'm going to go 2 times 4 is 8, minus 1 times x is 1, so that's positive 7. Let's see, 2x squared plus 8x minus 1x minus 4, yep. And then the zero product property lets me say 2x minus 1 equals 0, so 2x equals 1, so x equals 1/2, or x plus 4 equals 0, so x equals negative 4. Are both those solutions valid? Turns out no, because I'm taking log base 4 of x. Can I put a 1/2 in there and get a value? Sure. Can I put a negative 4 in there and get a value? I cannot. There's nothing I can do to take 4 to some exponent to make it negative 4. I can't have a negative argument within a log. So that gets canceled, and the answer is x equals 1/2. Almost there. 15. We've got log base 3 of 9 over 196, and we want to express this in these terms, which means we can use log base 3 of 6, we can use log base 3 of 5, we can use log base 3 of 8, we can use log base 3 of 7, and of course, we can use log base 3 of 3, because we know that one's 1. So I'm going to factor this. I'm going to treat this as log base 3 of, what does 9 factor into? Well, 3 times 3. What about 196? Okay, I'm going to make a factor tree here because I don't remember these offhand. So this is almost 50 times 4. It's 49 times 4. 7 and 7. Okay, I didn't get 4 though. All right, 2 and 2. So I'm going to go with 7 times 7 times 2 times 2. Now I can use the log base 3 of 3. So this is fine and this is fine. I can use the log base 3 of 7. This is fine, this is fine. But these 2's are no good for me. 2 times 2 is 4. If I can multiply an extra 2 down here, I can get that 8. So that's what I'm going to do. I'm going to multiply times 2 down here and times 2 up here. It's going to keep the fraction the same, but now what I've got is, I'll still use this 3. I'm going to combine this 3 and 2 here to make a 6, because now I did 9 times 2 is 18. On the bottom, I'm going to have 7 times 7, and then 2 times 2 times 2 is 8. And notice that now I've got all the values I want. I've got a 3, I've got a 6, I've got 2 7s, and I've got an 8. And so I'll write this as an expanded form log. Log base 3 of 3 plus log base 3 of 6 minus log base 3 of 49. Well, let's say 7 squared just to make it easy. Minus log base 3 of 8. Log base 3 of 3 is 1. Log base 3 of 6 is a. Log base 3 of 7 squared is the same as 2 times log base 3 of 7, which log base 3 of 7 is d, so that's going to be 2d. Write it up here, 2 times log base 3 of 7, which is 2d minus log base 3 of a to c. So there's my answer, 1 plus a minus 2d minus c. All right. Thank you very much.